Hi everyone. We are finally ready to start working on solving equations. So the first thing that I want to make sure of is that we're really clear on the difference between simplifying expressions, which is what we've been doing, or combining expressions by adding, subtracting, multiplying, dividing. And what we're going to do now, which is solving equations. So equation versus expression. An expression basically just represents a number. There can be variables in the mix, but it still just means this is a number. So if I look at an expression like 2x minus 5, I might not know what its value is until I choose or find out what x value I should be using, but it has some numerical value and that's all there is to it. It's just a number. When we move on to equations, like that first one you can see down below, all of a sudden we have a complete statement. 2x minus 5 is equal to 8, not just 2x minus 5, some number. 2x minus 5 is equal to 8. This is an equation. The big difference is that instead of just representing some number, people want to think of that as representing some number, represents 8. What it is it's a statement with the truth value. It's a statement that's true if we choose certain values of x and false if we choose other values of x. It's possible to have an equation where there are no values of x that make it true. And it's possible to write up equations where any value of x makes it true. But the general idea is, depending what x you choose, this is either a true statement or a false statement. So when I look at the expression 2x minus 5, there's no true or false. It just is what it is. And whatever x you plug in, you're going to get a different value of that thing. So just a number, just represents a number. Whereas the second one represents a true or false statement. So when we talk about solving an equation or finding the solution set, we're looking for the set of all numbers that make the equation true. So this is set of all numbers that make, and I'm going to even be a little more general, I'm going to say the statement true, because we'll also solve inequalities, and it's the same idea. An equation, you're looking for values that make the equation true. An inequality, you're making the inequality true, but still we're talking about the solution set. What makes the statement true? So we're going to rely heavily on a couple of properties of equality, properties of this whole equal sign business. So if you have a statement, what we're looking at up above, this 2x minus 5 equals 8. I always think of this, I've always really liked the visual of balance. We have balance, right? So we have 2x minus 5 is equal to 8. They balance each other, and we need to maintain that balance. So the properties of equality are things that we're allowed to do that won't mess up the balance. So this is kind of similar to in expressions where we don't want to change their value. So we either multiply by 1 or add 0. But now we have the two sides of the equation to balance instead of just having to balance a single thing. So what we're allowed to do is add anything we want as long as we do it to both sides. So you can think of adding weight to the balance, right? I could add another 5 on this side. As long as I also add another 5 on this side, they should stay balanced. So the properties. You can add or subtract the same quantity on both sides. And this you can means you can do it without messing up your balance. It's still a true statement, or it's still true for the same x values after you've added or subtracted the same thing on both sides. And then the second one is that you can also multiply or divide both sides by the same quantity without messing up your balance. So if you decide you're going to take half of what's on the left side, so if we cut it in half, right, we take half of it away. This will still be balanced as long as you take half away on the right side. You could triple both sides, and as long as you really triple both sides, they'll still balance. That's the idea. So you can, have to be a little careful on this one, multiply or divide both sides by the same quantity. And here's where I'm going to be careful. There is one thing that can mess us up here, and it's not so much that it results in a false statement, it's just that we lose the which values of x make this true. So our goal isn't just to keep the scale balanced, it's also to keep information about x in the mix so that we can find exactly which x values will make the statement true. So what I want to say here is by the same non-zero quantity. So the problem being that if you multiply both sides by 0, yes, the scale is balanced, but it's also completely empty. So you have no clue about what x values would have helped you out when it wasn't empty. And our goal is to use these properties to wheedle our way down to the x values that make the statement true. Okay, so that said, I want to switch colors. There we go. But record things are in the way. Work on this equation down below, and hopefully some of this linear equations business is really review for everybody. It should be. If you're having trouble with it and you want a little support, let me know. So I'm going to start off with one that's pretty darn easy, just to remind you of a couple of things, and then I'm going to work my way up through the other ones. But I'm going to approach this in a very specific way. So this whole first section, we're not just going to look at linear equations. We'll look at quadratics and rationals and radicals. And the theme of this first section is, what do you do when your variable only shows up once? Because there's a really nice strategy that'll get you through any type of equation without having to think of them all differently, which you know is one of my big goals, to get you to see that big picture. What is really going on with solving equations, so that I don't have to try and memorize different tools for each one. So the trick with what to do if you're solving equations and your variable, so we're looking for x, shows up exactly one time. It says it's on, why won't it write? Oh man, I think I lost my stylus. The trick is inverse operations. So that might not sound very new. I don't know if people have used that wording or not, but that's always what we've done. But I want to think about this really specifically, even for messy equations. So I'm not claiming that this is the only order you can do things in. There we go. So we're trying to solve for x. But I'm claiming that it's a really good way to be able to think about things when you get stuck. So if your variable appears exactly one time, all you need to do is figure out what operations have in what order. This should sound familiar because I tried to pick on you about this a little bit with expressions so that you'd be used to thinking this way. So if I think, okay, I plug in a number for x, the very first thing I would do is multiply by 2 times 2, and the second thing I would do is subtract 5. I've even seen this book where they make a flow chart, which you could do if you want to. I kind of liked it, but I don't know if I feel like drawing one every single time. I plug in an x. The first thing I do is multiply by 2. The second thing I do is subtract 5. So if I want to solve, I'm going to, and then I get my 8 out of this thing. If I want to solve for x, I'm going to need to do exactly the opposite things in exactly the opposite order. So the first thing I need to do is get rid of the 5, since that was the last thing happening to x. So to do that, you'll add 5 to both sides. And you don't really need to show this step the way I'm showing it right now. As we work into pre-calc and calc, we pretty much stop doing that, but I'm not bother, it's not a bad step, and I really want you to have this clear picture of balancing both sides of the equation. So feel free to not write the plus 5. That's something that can be done in your head, but that is absolutely what we're doing. So all that will be left on the left-hand side is 2x, and on the right-hand side, I now have 13. So now, since this is a fairly nice simple equation, all we're left with is 2 times x. The question should be, how do I get rid of the 2? You have to use the inverse operation. So if it's attached by multiplication, you're going to use division. You get x equals 13 over 2. You should know how to check your solution. You should be able to plug that back into the original equation. 2 times 13 over 2 is 13, minus 5 is 8. I'm not going to walk through that every time, but absolutely, especially for test taking purposes, you want to be able to double check and make sure you got it right. It shouldn't be a surprise if something is wrong. Might be hard to figure out why. Okay, so I'm going to make these messier. And again, I do want to say that this reverse order of operations is not the only way to do these things. You could clean up the mess, distribute, run things through the parentheses, and I'll absolutely do that, especially when we have variables on both sides. But I really want to work this order of operations thing because people will forget how to do things, get stuck, make mistakes in solving, and I think a lot of it really comes down to this order of operations business, making sure you know what to get rid of first. Okay, so if I'm looking at what happens to B, if I plugged a number in for B, the first thing I would do is multiply by 3. I would then add 5. I'd be done in parentheses at that point, so that's my PEMDAS, right? That's my P step. I don't have any exponents in linear, so I'm down to multiply, divide. So the next thing I would do is multiply by 3. And then addition, subtraction, and I actually have both of those things showing up. So we'll just say this one 4 and this one 5. So what I want to do is first get rid of the 6. I don't think I like where I wrote these. Let me move them up. 2, 5, so that I can write down below this thing. Okay, so the last thing happening is I subtract 6. The first thing I'm going to do is get rid of that by using the inverse operation, which is addition. So I get 11 equals 1 minus 2 times 3b plus 5. The second to the last thing was the adding 1 out at the front, and that one might look a little tricky. And again, really, I'm not trying to take away the option of just going right away and saying, oh, I can combine the 1 out in front and then minus 6 at the very end. You can do that, but this would be the order of operations walkthrough. So if I'm adding 1, I want to get rid of it by subtracting, and that can be a little tricky for people actually because they see the minus 2. So there is a subtraction, but remember subtraction always could be thought of as plus and the negative is attached to the 2, not the 1. So the 1 really is added to the negative 2 times 3b plus 5. Okay, so we get 10 equals negative 2 times 3b plus 5. Okay, last thing happening in that statement is the multiplication. We'd have to do everything inside parentheses, then multiply by negative 2. So we'll proceed to dividing out negative 2. We'll get negative 5 equals 3b plus 5. In that statement, last thing happening is add 5. We're always focusing on the side with the variable. So 3b plus 5, the last thing we do is add 5. So to solve, the first thing we do is get rid of 5. 3b, and then last thing we have is b is multiplied by 3, so we'll need to divide that out, and our final answer is b equals negative 10 over 3. Okay, again, checking solutions, awesome, please do it. I'm not going to spend extra video time doing it, but if you need me to remind you ever about a check, just let me know. I'm happy to go over it with you. All right, so let's get some fractions in the mix. That tends to always be a tricky thing for people. So what I see here is if I'm plugging in a number for A, the first thing I do, remember fraction bars are grouping symbols. So the first thing I do is deal with the top, which would mean I'd multiply by 5, or you could think about multiply by negative 5, and then I'd add 6. After that, I would divide by 8. And then last thing I would do is subtract 2. 1, 2, 3, 4. So I'm going to go reverse order of operations to get rid of them. I want to undo the subtraction. So I'm going to add 2 to both sides. I'm going to get 6 minus 5a over 8 is equal to 3. It should be an A. Okay, looking back now, the next thing that I need to tackle is the division by 8. To get rid of division by 8, you would multiply by 8. So this should just make the 8's cancel, right? We were dividing, we multiply, that should be gone. 6 minus 5a is all that's left. So 8 times 3 is 24. 2 things left to go. The last thing happening now is adding the 6. So we'll subtract 6 from both sides. We'll get negative 5a equals 18. And then very last step, I need to divide both sides by negative 5. Since that's attached by multiplication, we'll remove it by dividing out 5. And that's my answer for that one. Okay, last one, and it's a mess. If you haven't already, this would be a great one to pause and see how far you can get into it. And then you can come back and watch. But remember, I am going to do it the order of operations way, not the only choice. So I can say on this one, if I wasn't trying to specifically follow this reverse order of operations, another option would be to distribute the 1/5 through the parentheses, and then you could combine some like terms. So you could simplify the left-hand side before you tackle reverse order of operations. But I'm just going to go for it so you can continue to see how that looks. So I will have 1/5 2/3 g plus 1/10. Oh, I'm not writing this the way I was. Okay, so my first step, let's see. If I was to plug in a number for g, I'd multiply by 2/3, I'd add 1/10, I'm done in parentheses, so then I'd go back to multiplication again, and then subtraction. So the first thing I want to do is add 4 over 15 to both sides. I was getting into it too quickly. Okay, so I have 5/6 plus 4 over 15. And you will find as we move into other sections and I kind of free us up a little to manipulate things before we do reverse order of operations, that a lot of times what I like to do is just get rid of all the fractions right away. So that's totally an option. You'll see plenty of that in the next section, but I'm going to stick with my, my messy reverse order of operations for this problem. So I need a common denominator to simplify the right-hand side, and it looks to me like it should be 30. So I'm going to get 25 over 30 plus 8 over 30, which is 33 over 30. 8, 25, yep, and that actually reduces a little to 11 over 10. Okay. On the other side, I'm now down to the last thing happening being the multiplication by 1/5. So first you do everything in parentheses, then you'd multiply by 1/5. So to undo that, we need to divide by 1/5. Remember, and this works for integers as well, multiplication and division are related. Dividing by something is always the same as multiplying by its reciprocal. So I'm going to write it that way just to make it easier to work on the other side. So I'm going to multiply by 5 over 1. So the left-hand side now has a 2/3 g plus 1/10. The right-hand side I can reduce a little again. I can cancel out a 2. Is 11/2. Okay, so we're getting low on operations here. There's only 2 things being done to g on the left-hand side. The last thing would be adding 1/10, so we'll subtract that, and we'll say 2/3 g equals 11 over 2 minus 1/10. And again, this is what I was saying. I was writing the operation below and then the equal bar. You don't have to do that. It's okay if you want to do that, but as we move on, we definitely kind of start to move away from showing those steps. Really, that's just laziness, not that they're bad to write. Maybe that's an exaggeration, but getting a little bit shorter in the amount that we have to write does become a little more of a priority as we get more comfortable with operations. Okay, so I'm going to move up here, 2/3 G, and on the other side I see 55 over 10 minus 1 over 10, which is 54 over 10. I can at least cancel a 2 out of that. 25, 26, 27, 27 fifths. And then the last thing I need to do is I have 2/3 times G, so I'm going to multiply by 3 halves. 3 halves, and I get G equals 27 times 3, which is 81, over 5 times 2, which is 10, and there's my answer. Okay, so that was a reminder on some messy linear equations, some not so messy, and then some fairly messy. So hopefully that'll get started on those, and we'll work some rational in the next video. Thanks for watching.